Okay, so in this video, we're going to be looking at conducting a chi-squared goodness of fit test. Now, typically these kinds of tests are done on binned data or on discrete data to compare, typically for things like probability distributions, things like testing whether or not our results are distributed binomially or distributed as a Poisson distribution or distributed as a normal distribution or various things like that. In our example, we're going to be looking at a binomial distribution. But let's walk through our example and see how this works. So when we enter this data into our calculator, we're going to need to enter them into the lists. So we're going to begin by entering the data we have into our calculator. So you'll go to the stats menu and then scrolling over, or actually you don't have to scroll. The stats menu on the edit screen, which comes up, you'll just hit edit, hit enter. And then in L1, you're going to list these outcomes at the top of our table. And then in L2, you're going to enter the expected observations from each of these values. So let's actually walk through the example and show you how all of this works. So here's our example here. So the number of females in the litter is 0, 1, 2, 3, and 4. So below is a table of data for the sex of kittens and a sample of litters of 4 kittens. The data collected is below. The number of females in each litter should be distributed binomially with p equals 0.5. Again, roughly speaking, conduct a hypothesis test to see if the data fits that model. So the observations here for the number of litters is 13, 30, 94, 50, and 18. And so you can think of the top row here as our labels, and they don't actually contribute to the statistics, although they do help us calculate the probabilities or the expected counts that go in the expectations table. Now, unlike the chi-square test of independence, here, because the expected table is not just automatically calculated for us, we are going to have to calculate that ourselves. And that's partly due to the fact that this chi-square test can be used for many other scenarios than just a test of independence. So the observations 13, 30, 94, 50, and 18 will go into L1. I have another video on entering data into the TI if you need guidance on how to enter that data into the list. But basically, you would go to the stat menu, and then from edit, you would enter this data into the list, into list 1. Now, list 2, we're going to have to put the expectations. But in order to do that, we're going to need to calculate those expectations. Now, we're comparing the data we have to the binomial distribution. Now, the binomial distribution has this general formula. In this case, our probability is, there's a typo here. Our probability is 0.5, and our formula is going to simplify because normally this would be p to the x and then 1 minus p to the n minus x, 4 minus x in this case. But in this case, we have actually 0.5 in both cases, and 1 minus 0.5 is still 0.5. And so this probability will simplify. The two x's and the exponent are just going to cancel. The main thing that we need to worry about for this example is going to be the counting, the number of times that type of thing can occur. You can also use the binomial PDF function from the distribution menu to do this calculation. That I have also described how to do that in another video. But basically, you would select it from the distribution menu, which you can find by hitting second vars. And then you would use this distribution with each of the x's from the table 0, 1, 2, 3, and 4, going into the last position, this the binomial PDF. So it would be 4.5, and then you would do 0, and then you would recalculate it for 1, and then you would do 2, and then you would recalculate it for 3, and so on. So I've obtained these values for the distribution, and I've done the first example here for those probabilities using the binomial PDF that I've gotten from my distribution menu. I have put in the 4 for the number of possible females in the litter, 0.5 for the probability, and then we would go through, we would do each one of these. 0 converting to a fraction gives me 16. If I put in 1 and then convert to a fraction, I get 1/4. If I put in 2 and convert to a fraction, I get 3/8. If I put in 3 and convert to a fraction, I get 1/4 again. And then if I put in 4 and convert to a fraction, I'm back to 1/16. Now, in our original data set, we had 205. If you add all of these up, you get 205 litters. And so in order to calculate the expected value, you would take each one of these probabilities and multiply by the total number of observations, which is 205. So in our lists menu, again, we would go to Stat, hit Edit, and then in List 2, we would take our probabilities, 1/16, 1/4, etc., and we would multiply them by 205. So 1/16 times 205 gives me approximately 12.8. 1/4 times 205 gives me 51.25. 3/8 times 205 gives me 76.8 and change. 1/4 again times 205, and then 1/16 times 205. So those are the expected number of litters with various counts of the number of females in the litter that we would be expecting from a sample of 205 litters. So once that information is entered into list 2, then we can go to the stat menu and then the test submenu and look for our goodness of fit test. So this is the chi-square goodness of fit test. It is D on our list of tests. Again, you can get this faster by scrolling up to the bottom of the list and then up to D instead of going down to D from the top. But either way, the D is the test that we need. Now, once we get into the output, the table where we're going to enter things, these are the screens that we're going to get when we enter the goodness of fit test. The observed are the data that was given in the problem. That's our list 1. And so we would type that in by hitting second 1. And then the expected list would be where we calculated those probabilities times the total count that we were estimating from the binomial distribution. That would go into list 2, so second 2 here. And then the degrees of freedom is 1 minus the number of bins that we have. So if you go back to the original problem, 1, 2, 3, 4, 5. So there's 5 total categories, and therefore the degrees of freedom is 1 less than that. So this would be 4, and then you'd scroll down to calculate. And when you run that, the output screen will give you, again, the test statistic, the p-value. It'll restate the degrees of freedom, and then you can basically ignore this last line down here. Now, the p-value is the main thing that we are interested in. Our null hypothesis for the goodness of fit test is that the population is distributed according to the distribution we're comparing it to. So in this case, the null hypothesis is that it is binomially distributed, and the alternative is that it is not binomially distributed, because that was the assumption that we made for our expectations. Now, this p-value is less than our standard p-values. It's less than 0.05. It's less than 0.01. This would suggest that we would reject the null hypothesis. And in this case, we would say that the data does not appear to be binomially distributed because our p-value is too low. If the p-value is high, then we would conclude that the difference between the binomial distribution and the data we have is probably just due to random chance. and it's close enough to a binomial that we're good with it. But this would seem to indicate that this is not distributed binomially, or at least not the binomial distribution that we were using to do the expectations.